we've been doing a lot of rotating around the x-axis. So let's start rotating around the y-axis and see what we can do, or at least attempt to. So let's say, let me draw my axes. That's y-axis. That's my x-axis. And let's say, well, let's just do it with an example. But we'll call it f of x too, because it'll be generalizable. Let's just draw, I don't know, y equals x squared. Something like, let me just draw the positive, because we're going to rotate around the y-axis and it's symmetric anyway. So that's y equals x squared. Right? This is y-axis. This is x-axis. Actually, no, I'm going to keep it general, and then we'll actually solve it particularly. So we'll call this f of x, but clearly this is y equals x squared. This is f of x. And we know how to take the volume if I were to rotate this around the x-axis. But what if I wanted to say, well, let's say I guess we could call it the area between 0 and, let's actually just say between, well, let's say, I'm trying to determine how general to be. Let's just say between 0 and 1. I think the boundaries might make sense to you. So this, roughly this area, and I'm going to rotate it around the y-axis now. So I'm going to rotate it around the y-axis now. So what's that final figure going to look like? It's going to look something like let's see, the base of it. Let me see how well I can draw it. It's going to look like, nope, that's not what I wanted to do. The base is going to look something like a cylinder like that. And then the top of it is also going to be, no, that's not what I wanted to do. Draw the sidelines. So then it's going to have it's going to look something like that. Something like that. And then the top of it, something like that. And then, but it's not just going to be a cylinder, right? If I was doing this entire block, it would be a cylinder, but the inside of it is going to be kind of hollowed out. So let me see how effective I am at drawing that. I'll do it in a different color. So the inside is going to be hollowed out. So it's going to, I don't know if that makes sense to you. That it's kind of like, you could almost view it as on the inside it'll look like a bowl, on the outside it will look like a cylinder or a can. Hopefully that makes sense. You take this and you rotate this around, and the curve that specifies the inside would be y is equal to x squared. But it would rotate all the way around, like if I were to draw it that. I think that makes sense. The drawing is the hardest part. So how do we do it? Well, even the shape might give you an idea. We can't use the disk method, and what we were doing before when we were rotating our x-axis, that was the disk method, because we were essentially imagining each of these particular disks and then summing them up. Now we're going to do something called the shell method. So what's the shell method? What we're going to do is we're going to take, instead of taking a bunch of disks and figuring out their combined volumes, we're going to take a bunch of shells. So what's a shell? So imagine a rectangle right here. Hope you can see it. Right there. Let's say it's at the point x1. What's its height going to be? Its height's going to be f of x1. F. That's its height. Now imagine taking that sliver and rotating it around the y-axis. What's it going to look like? Well, it's going to look like a shell. It's going to look like a cylinder, just like the outside of a cylinder. Let's see how well I can. It's going to look not too different than that, but I want to draw it well, because the intuition is the most important thing, not getting the problem right. Let me see if I can draw this respectably. Then we're going to have the bottom of the shell. Looks like that. Let me finish these lines up. I think you get the point. You don't have to be. Okay, so it's going to look like a shell like that. And let me see if I can. So the outside of the shell is going to be solid, right? And it'll have some width, right? But the inside is hollow, right? Let me do a different color, maybe a darker color to show that's the inside. It's a hollow, it's like a ring essentially. And so what's the height of this ring? Well, I took this, the height is going to be f of x1. So let me do a brighter color so you know what I'm saying. So the height of this ring is f of x1, right? F of x evaluated that arbitrary point we picked up. what is going to be the surface area of this ring, this outside? Well, let's think about it. It'll be the circumference of this ring times its height. So what's the circumference of this ring? Well, circumference, let's go back to our basic geometry. Circumference is equal to 2 pi times the radius. So if we know the radius, of it, we know the circumference. Well, what's the radius? Well, the radius is how far we went from the axis of rotation to that point. So that's the radius. So in our particular example, the radius is x1, right? The radius is equal to x1. It's that x point that we're evaluating it at. Right? So circumference is going to be equal to 2 pi times that point that we're evaluating at. And so then the surface area, this magenta thing that I filled in, that's going to be equal to their circumference times this height, which we already said is f of x1. So we could say, let's call it area surface. Surface area is equal to circumference times height, which is equal to 2 pi x1 times f of x1. Alright, so we figured out the surface area of this. Now how do we figure out the volume? Well, the volume of the shell, well, what's the width of it? How thick is this ring? What's this thickness right here? So, it's a very small thickness. But we took this sliver, and the sliver, as we learned in previous calculus, the width of this little rectangle is dx. And when we take the integral, it's going to get infinitely smaller and smaller, and we'll have infinitely more and more of them. So the width of this is dx. Right? Let me draw it big. That's a horrible looking. So if this is a sliver, that's the sliver. Its width is dx. Its height is f of x1, right? X1 will be right in the center. And then its distance from the center is, of course, x1. Hopefully that makes sense. So what's the volume of this shell? So the volume of the shell, this shell, not this one, the volume of the shell is going to be equal to the surface area of the shell times how wide that surface is. And that width is dx. It's going to equal this times dx. So the volume of that shell is 2 pi x1 times f of x1 times dx. And I think you see where I'm going with this now. So what would be the volume of the entire rotated figure, this thing here? Well, I'm just going to sum up each of these shells, right? I have one shell there, and then here I'll have a slightly less high shell, and up here I would have a much bigger shell, and I'm add them up, right? Here's one shell that goes around, then there'll be another shell here, and I'll add them all up, and that's taking the integral. So the total volume of the figure, when I rotate it around the y-axis, is going to be, and my boundaries are from 0 to 1, 0 to 1, 2 pi, this one I just showed you a particular x1, but we're going to sum them over all of the x's. So it's going to be 2 pi x, f of x, dx, right? This is just a constant, so you could call it 2 pi times x f of x. So let's take a particular example. Let's do it for x squared. Let's say the function is x squared. So in this case, the volume is going to equal, let's take the 2 pi out, 2 pi integral 0 to 1 x times f of x. F of x in our case is x squared, which I drew earlier. Dx equals 2 pi. This is just x to the third, right? X to the third. So it's going to be 2 pi times the antiderivative of x to the third. Well, that's x to the fourth over 4. Evaluated at 1 minus it evaluated at 0. Well, that equals, and I think I'll have enough space, 2 pi times, well, 1 to the fourth is 1, so 1/4. And then 0, well, minus 0. So it's 2 pi times 1/4. So that's pi over 2. Pi over 2. That's the volume. Just rotate it around the y-axis. I will see you in the next video.